We are jumping into discussion on mutual inductance. When the current in a coil changes, the generated electromotive force EMF in another coil loop is called the mutual inductive force. This is called the mutual inductance phenomenon. Consider this situation. The first coil is the primary coil and the second coil is the secondary coil. They are both fixed in space. When there is a current in coil 1, the magnetic flux generated in coil 2 equals N mutual inductance 2-1 times the current I1. When I1 changes, the EMF depends on time, namely EMF 2-1 equals minus d phi 2-1 dt, and it also equals minus n 2-1 di1 dt. So basically, n here is a coefficient that represents the relation between the EMF and the change in current. Now define the mutual inductance as N21 equals phi 2-1 over I1. This is our first definition. And our second definition is M21 equals minus EMF 2-1 over the change in current I1 dot. Similarly, when there is a current in coil 2, the generated magnetic flux in coil 1 is phi 12 equals M12 times current I2. When I2 changes, the EMF in coil 1 is minus d phi 12 dt equals minus the mutual inductance 1 to 2 times the change in current di2 dt. And of course, the mutual inductance is N12 equals phi 12 over I2, or it also equals minus EMF 12 over I2 dot. And here are some symmetry conditions. We know that the B field is the curve of the magnetic vector potential A. We can also write flux phi 2-1 using the curve of A integrated by the closed surface. Then we apply Stokes' theorem to find an explicit expression of the flux. Then, with the expression of phi, we divide by I, we can find that N21 equals phi 2-1 over I1, and also equals some constant multiplied by the stack of two path integrals. Since the labels of 1 and 2 are interchangeable, then we get M21 equals M12, and this is the symmetry of mutual inductance. We obtain this result fairly because the two coils are fixed in space and they are separated by the same distance.